Okay, everyone, I guess we're live. We'll wait, I think, half a minute for people to come in. Take a note of the chat as well. There will be Q&A and some prizes to win. During the lecture, I will ask the questions that you may answer in the chat, and then later we will draw someone who answers correctly on the questions to win the prize. All right, I think we can start. Welcome everyone. This is TWF. This is our fifth meeting on the on our series, on our meetups. This is the way forward, and well, the goal is to share the knowledge and spread like the newest things on IT in this series. So stay tuned to our meetups. This session is about neural networks and especially how we used it in driving a robot. So you will probably hear something about the segmentation neural network, especially how it works. I'm assuming more or less that since you're here or hearing about well, you're interested in these topics and you know more or less what the neural network is. If not, then we'll do a very small recap in the middle of the session, and then I'll talk more about the robot and the plan how to do that. All right. So this is this robot was developed during my work actually, and it started as a real life project. I will tell you more about it a bit later. You used computer vision to steer the robot, to control the robot. Yeah. More about me. I'm an Avanade employee. 10 years more or less in software engineering, plus now I'm working as a machine learning specialist also at Avanade. This is the fourth year in this lovely company. I'm as a hobby, I'm doing other things like creating stuff. This is what I like to spend my time on in the evenings. Using 3D printing, electronics, and well, the Arduino or other microcontroller that may fit into the project. You'll see an example here in this session. All right, so let's start about the project. So this was really a live a business example, as you might think later. This is like an amateurish project, but it really started as a business case. So we were doing a project for well, POC for our client that needed to improve its health and safety in the warehouse. So that the trolley was driving in the warehouse. We were trying to come up with an ideas with how to steer the robot using only visual input. This is by the way not a standard way of doing it, but this is how we tried to approach the problem. It ended up basically in this stage of POC, and later I picked it up also. Well, left in most of the code in the company, but this small parts that I used in to steer the robot and to with the neural networks, I moved into my side project, which I will show you today. So this trolley actually uses this visual input. It had like a lane drawn in on the floor using tapes. So we thought that we might have it's easy to replicate this environment, and because I like to build stuff, I built my own robot. So it's if you know what you're doing, it's not that hard actually. The heart of this robot was Jetson Nano, for which you can see, well, barely, but it's there in the middle of this robot. On the sides you have a microcontroller that is also connected to this Jetson Nano, and this is used for controlling the DC motor controllers, which are steering the engines, the drives, and the wheels. So we have here like four separate drives. And this is all powered by LiPo battery, and in the bottom, well, actually the camera is there as well. This is actually quite important because it has a wide angle camera. Without this wide angle, you cannot really steer. You cannot really steer. Oh, I'm seeing in the chat someone's not seeing the presentation. That's good. Hopefully it will resolve. Wide angle camera is needed if you have this small robots, because you need to see broader than usual, than you might think. This usual like 90 degrees cameras are not a good fit for this kind of a project, so you need a special one. And in the bottom there is a LED with line following sensor array, but this is for like later. I use this robot as a base for other experiments. This is not used for this project. And by the way, I am still working on it, so it's more often than not in a service, not working. So like right now. All right. And for this project, we also, besides the machine, we needed an environment to replicate somehow the environment. And this was not that hard. I just used a taped version of my floor in the apartment. A couple of features that I wanted to have that would replicate the real environments. some turns that the soft turn, the hard turn. The hard turn turned out to be, oh, there are no slides. All right. Okay, so let me go back and try to do something more to it. Perfect. So let's then do, sorry for that. We'll do this and give me a sec. Mm, we'll resolve that in a second. Um, we're almost there, I think. All right. I think that it should be almost this one, and we'll do this and some maybe slideshow. Slideshow is here, and there's a view here, and this reading pane, reading view here. All right, you should see now something more, except me. Can you let me know if it's working? All right, this one, and we have, yeah. All right, so just to quickly update you with the slides. So this was a computer vision. This was about me. The background. And the view of the robot finally. Okay, so the Jetson Nano here in the heart, the wide angle camera, motors, and Arduino, plus the power with the LiPo battery. There are slides with the turns that I was talking about. This 3 lines should support with us with ending of the roads, which robot might recognize. And there is the because like the simple road isn't enough for us, and the real world comes with challenges. That there is a pedestrian crossing as well, which happens on the warehouse floor. The off-road artifacts that may not be confused with any obstacles. This is what we want to avoid. And a crossroads where the robot in this instance will go straight, but not to also must not confuse the robot. All right. Uh, so again, back to how the robot understands the environment. We used something that is called segmentation network. So this is a segmentation task for neural network, and this is segmenting the view in three layers or three classes. Each pixel is given a class, and we want to recognize where is the road. This is the red region on the left. Where are the tapes, and where is the obstacle. So to do that, I'll talk later how to do that. And the other part of the robot is its steering system. This is PID system that is used to detect where the robot should go, and you can see like this red and yellow dots. We'll see how it plays out. So basically, the robot drives until it sees something that resembles an obstacle. Then the obstacle detection system hijacks the control signal for the driving and stops the robot. We cannot remember that the original idea was to improve the health and safety, and we wanted to have something that will stop the robot if it sees a human or an obstacle of other kind. And so this is doing exactly that. The obstacle detection is actually this is my mesmerizing GIF. Hopefully you can see that, and it's showing how the network, although not perfectly recognizing the road and the lines, is recognizing and stopping the robot in case of detecting the obstacle. So this turned out to work with the robot. Sorry. All right. And the other. Oh, sorry, sorry about that. All right. So the other part that is actually steering the robot is the PID controller. So this is the mathematical mechanism that is behind this following the roads, and all right. So something is not there. I'm guessing. Okay. So let's see. Try to fix that. This right part. Okay, and we'll do. Now it's much better. All right. So on the right side again, you'll see this red dot and yellow dots. That is and the robot is trying to match with this PID controller the red dots, which is always in the middle, to where the road is, which is detected by the other way around. This yellow dot that is in the middle that's to the red dot, which is the middle of the detected road. Okay, so how do we actually approach this this segmentation? How do we create that? So there are basically 3 steps to do that. Each of them has its own set of challenges. So this first of all, you need to have a data set for the model to train. And label it. So this is like the first slide on the left. Then you need to have the model itself that to then find the best one, somehow train it and find the best that suits your needs. And the last one is actually not that obvious, because what I thought at the beginning is that when you have the model, you just put it in the device and run it there. So it's not that easy due to some constraints that you have in terms of memory and the speed of the inference. So we'll see how to overcome also this. So what was actually the constraints? The constraints was that we needed to run this model at least 4 frames per second. That is to have enough frames per second for this PID to run. And it turns out that 100 milliseconds more or less is needed, or this is like the high boundary of how much we can spend time on the model itself, because the other parts of the pipeline also require some time. The inference part on the neural network has to fit into this 100 milliseconds, which is quite challenging, I think. Quite challenging after when you think about it. This is if you run the model on the CPU, that may not fit into this one. So that's why we chose in the very beginning this Jetson Nano, which is a hardware that has GPU on board. This is something that is very unique to this hardware, and this hardware is actually not random hardware. This is NVIDIA GPU. So you can view it as a small computer. People actually use this Jetson Nano to stack them and run some serious pipelines. It has 4 gigabytes of memory to use in the on this card, so it's quite powerful for its size. Alright, if we go back here, you can see this Jetson Nano. Oh, yeah, barely, but it's there. Jetson Nano in the middle, but on the very top you can see LED button, and this LED button actually helped me with the first part of getting the pictures for retraining. So I gathered 170, almost 180 of images like this. So just pressing the button and the Jetson Nano will save whatever the camera sees right now. and this way I created a label a data set that I will label later for the retraining. The labeling itself is actually quite easy if you have the tool. So there are quite a few brands of out there to label things. So one of them is the labeling studio. Azure has its own tool. There are many commercial ones. If you start labeling, you will see why it's a big business in the modern AI. This is very tedious, very time consuming, and whatever improvements you can make on the labeling, this will be that cheaper. So people are doing tools that partially, at least, automate this process. There are big businesses around employing people to label the data for you. So if you try to do it on scale, then you have a couple of options. These commercial tools will allow you to use even AI to label, to train the AI. So it's quite fascinating. Anyways, my task was to label every image like this. So this is the picture from the robot, and I had to show the labels for the road, for the obstacles, that is in the yellow here, and for the tape. There is a question if Jetson Nano is used also for training too. Yes, it can be. This is one of the ways people do it. We used for the speed only cloud resources, but in the last part, on this last part where you had to optimize the model for the inference, there must be this Jetson Nano present, and I'll tell you why later. Okay, so there is a quick recap of how the convolutional layers and neural network actually work, so that you are not left not understanding what we have. But we also told that there will be two questions about the presentation, and one of them, the first one, is what is the name of the controller that is steering the robot and keeps it on the track, and the other question is, what is the name of the framework that we used here to optimize and do the inference of the network on the Jetson Nano itself. All right. I hope that this question will come up in a second in the chat as well. Okay, so this convolutional layer is, if we go back to this slide for a second, we need a neural network, a special type of network that is capable of doing segmentation. So we need to, in order to understand what is this segmentation, we need to go back to the convolutional layer and how the neural network work. So neural network, you probably know something, heard something about it. This is a set of neurons combined in layers, feeding one to the next usually, and this network obviously has some inputs. Then there are a couple of hidden layers that are this middle layers, and the output layer, which where you read the output and see what is the result. These layers are actually in the memory represented as matrix, and each of these like fields in the matrix is called a weight. A weight is a way to describe what the neural what the neuron knows about how to sum up the, its inputs. So the mathematical way to describe the network is actually set of matrices that are computed, and then this data comes out as an output. On the other hand, if you want to train the network, you will have to because you know the expected output. So for example, in here we know how the what is the expected class of the pixel. So we know we can and this is also a matrix, right? So we can represent each image as an set of pixels, which can be then transferred into matrix, and this output from the neural network can be we can compare the output of the network with the image that we have, and this way we can say what is the error of the network. Then we compute back using the same matrices, and we go back with this error. This algorithm is based on gradient descent, and this way we can update the weights eventually. Yeah. Okay. I see some good answers in the chat. Okay. So we know more or less have like an imagination of how we update the weights, and this convolutional layer is a special type of layer. Let me show you the other maybe slide that will give you some insights how it's used. So we take some part of the input and process it with the convolution. So like here on this example on the bottom, you have special some inputs, and then give it some kernel filter, and then it gives out this nice image on the right. As convolution is used in the neural network to learn what are the features of the images that it has, and works like this. So you have the image 0 1s in here. You take a patch. So this is like a part of this image, and multiply it with the kernel filter. Kernel filter is something that this is the learnable parameter of the neural network. So this is the matrix that will be updating during the training, and the neural network this way finds its own like set of kernels that gives some features, finds the features of the images, and it's computed like this: that you multiply the patch with the kernel and then sum up everything. If you can do like quick math here, 9 plus 7 plus 5 and 6, 3 and 1 will give you 31, and you do that for each element in for each place in the image. So you slide this window to the right and to the down to the bottom, and end up with an output like this. This is, as you may see, this is smaller than the input matrix, because you slide it 1, 2, 3, 4. This 3 by 3 will fit in here only 4 times to the left, and to the bottom it will also fit 4. So the output is 4 by 4. And if you are wondering what is this kernel, or what kind of features can you take, how can you use that? There are certain kernels that people studied, and one of them is a Sobol, very well known way of extracting the edges from the image. So this is like handcrafted, but neural network has this ability of learning this kernels on its own. It doesn't have to use anything that is previously given to it, like this Sobol kernel. It will learn it by itself. Alright, and what we got usually in the neural networks is multiple layers of this convolutions, usually divided into subsampling. This image has a small error on it, so like you can imagine that you can stack multiple of this convolution on top of itself. So if we take it from the left, then the input image will we extract some feature maps with this convolutions in the beginning, and in this instance we have we managed to learn four of this kernels, so that they are represented here as 4 separate feature maps. Usually the network is divided with this subsampling layer, which is very similar to what we do with the kernel, but instead of multiplying by the kernel, we take like a maximum from this image. This is here we have only zeros and ones, but usually in the non-black and white image you will have multiple values here. So you may have like 0.5. You take a maximum from this patch, and you just lower the resolution. This is of course create new feature maps. In here, in this example, you have like 4 feature maps on the left, and after subsampling there is 5, which is an error. and then you can apply on each of these feature maps subsequent convolutions, and you have more and more of this. So in the end, if you have, for example, that if you want to classify this image or do the detection, in the last layer you do like squeezing. This is all of these subsamples, and provide it into a fully connected layer. This is a layer that doesn't have the convolution. This is the simplest layer you can get. And this layer actually, what it does is compute the probability of this image being into the class. So this is what it learns to classify the pixels and give it some output. In the segmentation model, you actually don't have this fully connected layer. What you do is replace this fully connected layer with another convolution, and this way you'll get here like a squared output. And the squared output, you may have multiple of them. Usually what people do is output as many as there are classes in the we had like this three classes: the road, the tape, and the obstacle, plus the background class, which is also used. So we would have three classes basically, and each of the outputting feature maps will tell us what is the probability of this pixel being in the, for example, road class. And from this four, we classify these pixels as the one of being of the highest probability there. So like 100. This let me go back here. This pixel like in the middle may have a probability of being 0.1 in the obstacle, 0.2 in the being a tape, and 0.9 in the being road. So we'll classify this one as a road, and this is how we get the probability for each pixel in the image. All right. So we go back to this slide with our plan how to create and how to run this segmentation model on the Jetson Nano. First thing, label, we have that covered. Second thing, to get the model, actually you don't even try to at this point to write your own segmentation model. There are multiple of well-known models that people studied, and they are described in the papers. So we use that. There is a repository for PyTorch, which is like my framework of choice for neural networks. And the segmentation model is a repository, and there are very many segmentation models there, where we can train them and compare how they behave on our data set. One thing to remember is not to start from the beginning in the learning as well. So this is This is something so that people usually think that you need to retrain all the network. This is not the case. To speed up the training process, you need to we have this technique called transfer learning. So you take a trained version of a network, and what you do is freeze some of the layers, freeze some of the first layers, and then retrain only the last part. You can even substitute this one with like a random weights and retrain it on other labels. So this is what we did. You can see here in this example, there are a couple of convolutional layers in the beginning, couple of this dense layers, which is they are also called fully connected layers. We didn't have that. We did have this segmentation network. So we did have some of the convolution layers on the end. But the principle is actually the same. So you freeze some of the first layers, and then those frozen layers then doesn't get updated during the training at all. This saves us some time because you don't have to do the computations on this first layers. Plus, it saves some memory because with the training of the layers, there is additional memory component to it. So all you have to do is quickly update the couple of last layers, and that's it. And you may wonder why this actually works. Why we have to train on the last layers while the first ones are frozen. So the answer to this question is that this first layers has this features of the image captured. So you may imagine that the first layer gets this Sobel filter, and it detects the edges. The second layer will have like a higher level abstractions capture. So you may see there that there are some corners, bigger corners, or if you want to detect like people faces, then it may have like eyebrows or something like that. Then the next layer will capture even higher dimensional features like the whole eyes, the nose, a chin, something like that. And turns out that if you have the network that is trained on a big data set, like here from eyeballing, this one is a COCO data set. So this is a very well known and tried data set available in the internet by Microsoft. And if you have this kind of network that is very deep and trained on this data set, this first layer, first couple of layers tend to learn something that is universal across the images. So by the way, this is a nice reference to how the human can see. So there are a couple of layers like this of neurons right after your eye, and they tend to have the same structure that we do in try to replicate in the convolutional setup, and they from what we observe in from neurology is the same behavior that brain actually does the same kind of layering and learns as the same, like the basic features, and then more and more abstract. Back to the robot, we substituted this this last layer with a new head and gave it 3 labels. And this is how we trained I think about 20 of models that are available there in this segmentation model library. If you remember, there were some constraints there, so we picked only those that are small enough to fit our model, but I will also do some comparisons, show you some comparisons later, how we chose the best one, because it also goes through this optimization framework that is TensorRT. TensorRT is the framework for taking this network from the like the raw network from the PyTorch, from TensorFlow, from other frameworks, and run it, optimize it, and run it on the device hardware. TensorRT is especially good at running this one on CUDA, because it's actually their hardware, so they have this upper hand here, and there are other runtime and optimization frameworks that you can use if you are, for example, not blessed with having the NVIDIA card. You can use OpenVino from Intel that runs on the CPU very well. This modern CPUs usually have this component of graphical card on the chip, so it's using this part of the chip to run the network. It's actually quite easy to do that. But because I have here just some Nano, it's easier, and the best choice is right here, TensorRT. All right, so why actually again we have to go through this hassle of retraining of optimization on the TensorRT? This is due to the the speed actually. This is a slide that shows you the scale of the network. So there are multiple choices here from the smallest networks that's supposed to at least run very fast, and then to the big ones that has like over 800 mega of parameters. So in terms of performance, you can see if you run the inference on the PyTorch, there is this. I highlighted the 3 that will be seeing in the next slides as well. So if you do the inference on the PyTorch, that there is like 34 milliseconds, and you can gain 66% for if you do the optimization on TRT. The same for memory consumption. This is actually quite big. because the PyTorch uses up a lot of memory, and you can save a lot and then have the space for the other stuff that you may need during the difference. So you can save like 2 GB of memory here, and because this memory in Jetson Nano is shared between the CPU and GPU, then it's quite a lot in here. So we trained 20 of them, measured how they do. This is intersection over union. This is a metric that tells you how good the training was. So this is like a mid model and the very best model. Well, maybe not very best, but the good one that can be used actually here to detect the road. That the left one, although the metric is quite high, we need to go a bit further and do more training on it on this one. So as a side note, I wanted to just quickly tell you why we used like a real environment instead of a simulated one. You can see here that the colors are very good. The edges are very sharp and compared to the real one, and this is not usable for the camera inputs. You can simulate and test other things for self-driving here, but the camera is not good. We consider it heavily using the simulated environment, but this one is the only one that works in real life if you take pictures from the real environment. And skipping to the very end, we used this ResNet that had the performance around 130 milliseconds on the GPU. You can't see any others because we didn't have time. That the optimization on the Jetson Nano takes around an hour or so to do. So we checked the performance on CPU, and then if it was good enough, we chose this one, the best one, and then turned to TRT to do the optimization. Funny thing about this TensorRT is that if you optimize on one library, like we used 4.1 4.5.1 version, whatever. If you use any other version of the software, it won't run. So it tells you that you have to do the optimization on the very same device that you will be doing the inference. Hopefully this will work. This shows the end of its journey, how it performed. This is not the best run, as you will see, but it behaved this way constantly and without. You can see here that it went like right and left, but more or less it behaved very well. And this is the end of its journey. It will not stop, if you are wondering, and hit my door somewhere there, because we didn't implemented the stop condition. There are a couple of things that we wanted to do later, like obstacle avoidance and so on. I'm doing right now my own LiDAR and SLAM on top of it, so I printed some parts and bought the lidar and so on. So it's in progress. The overall we got this 190 for full revolution with this network that had like 130 milliseconds for the inference, so that was very good, and it behaved like this. Probably then you can do better if you want, and if you want to replicate it easily without building a robot, there are a couple of options. One to buy a JetBot. This is the same in terms of it has the Jetson on board, and it comes with some pre-installed packages where you can learn the stuff, including building and using the visual input. Of course, our code was custom, but they have pretty much also very very nice code with neural networks. The other option is to use some other accelerator with Raspberry Pi, for example this NCS2 that you can see here on the slide, or Coral. This is a Google one, this Google accelerator that will also run on Raspberry Pi, but then you will need to, of course, buy a platform that it will drive. The overall costs is about $120, which is over 1,000 zloty. By the way, this this robot that I constructed was supposed to be cheaper, but turned out to be much costly, especially because I had to buy a couple of cameras because I didn't know that it's so it has to have this wide angle. All right, we came to an end. It's I think it's Q&A question time, and this was TWF. You can of course reach us in the meetup. You can do the replay on the YouTube, and you can follow me on the GitHub. If you want to drop me an email, feel free. Try to respond. Okay, so we have. Are there any questions? You can ask them in the chat. Okay. Anyway, if something, you can save my email or drop me some messages. Find me on GitHub. There will probably a code for this this robot available, but I need to do some legal stuff before. But it's there, and put the license, things like that. I'll try to share this one as quickly as possible. If you want to take a look at it, and I won't do it in the next couple of days, again, drop me an email. I wanted to thank you for participation, and wish you a nice end of the week. Thank you very much.